All right, so let's talk about some interesting filtering examples. Now, this is your input image. You have seen this image a lot. So we are going to use this separately in this course. This is a very famous Lena image. And in this case, this is our kernel. Okay, so you can see the kernel is all zeros and it's one at the center. Now, I mean, most of you can easily guess, like if we have such a kernel and we perform filtering using this kernel on the input image, it won't change anything. The image will still remain the same. So if you try to visualize this kernel in two-dimensional, it will look something like this. The center is pretty high and all the other values are 0. And the reason it's not doing anything, because if you try to use the neighborhood values, it's saying everything is 0. So it's kind of enforcing that you don't use anything from the neighborhood values. Just use whatever you have at this particular location. And if you do that, it's kind of, you are not changing the image. So it won't change anything. All right. So again, but this is a filtering operation and this is a kernel. Now let's see some variation. Let's move that one towards the left. All right. It will look something like this. So don't worry about the orientation of this plot. It's just saying that, okay, now the weightage is being given to like a pixel, which is like neighboring of this, the pixel which we are interested in. Now, I mean, you can perform the filtering operation, which we discussed the equation, but if you try to think intuitively what's happening here, what we are doing is we are actually not using any of these values, right, in the neighborhood. And we are even not using the value itself in which we are interested in. But what we are doing is we are using the value which is on the left. So if we, Teja, can you please mute your mic? So if we use this value, then essentially we are actually taking this value and storing at this location. All right. So now what will happen is your image will shift. And you can see that since you are moving values from left to right, your image is going to move from left to right. It's just a shifting operation. So now you know that, I mean, using this kind of kernel, you can actually perform shifting in your images, which is very interesting because this is a very simple kernel, right? Similarly, you can actually have one at any other location and you can perform shifting. For example, if you have one over here, it means that you are shifting the image diagonally. Okay. Now, this is another interesting kernel. And in this case, what's happening is we are actually paying equal attention to all the pixels in this neighborhood. Right? And you can see here that we have this normalization factor, and that's due to like we don't want to mess up with the pixel values, right? So we want it to be normalized. And the normalization is coming from summing up all the values in this filter. Earlier, we didn't need this because we just have one. So if we divide by 1, it won't change, right? Usually we normalize our filter. So we have 9 different values and the kernel is actually normalized. In this case, what's going to happen is you're saying that if you're focusing on this pixel, please also look at all the other pixels in the neighborhood. All right, so let's see what's happening. It's kind of smoothing your image. So this is in a way like you can say a blur filter or a smooth filter. So it will smoothen your image. Okay, later we'll see like how this is useful. This is another example of the same blur filter. In this case, a filter is slightly bigger. This was a 3x3 filter. In this case, it's a 5x5 filter. All right, and again, you can see the normalizing factor. It's 25 because all of these values will sum up to 25. And again, you can estimate that what's going to happen. This is going to smooth your image. But if you compare this smoothing with the previous one, this is like much higher smoothing because you are considering like a bigger neighborhood. Right? In this case, it's 5x5. Earlier it was 3x3. You can keep improving the increasing the size of the neighborhood, and then your smoothing will keep increasing. Okay, so that was like a very simple smoothing filter. Let's talk about Gaussian smoothing. So this is a Gaussian filter, and you can see that the center of the kernel, it's pretty high. And as you move towards the neighborhood, the values are going down. So this resembles like a Gaussian kernel. but it's kind of a discrete form of Gaussian function. Okay. Now, again, if you perform like filtering using this kernel, you can see again, it's kind of smooth, but it's not very distorted. You can say like it's not that bad when you're filtering using like all ones. So this is slightly better than the previous filter. And that's one of the reasons why Gaussian filter is used in filtering. And the reason for this is you can see that whichever pixel we are focusing to, we are actually giving more weightage to that pixel. And as we move away into the neighborhood, the weights are going down. So it kinds of say that, okay, you're not completely ignoring the neighborhood. You are still using those values, but not that much. Okay. Now let's try to compare the smoothing operation using Gaussian and using averaging. So this averaging is like the filter which I showed you earlier, where you had like all ones. You are giving equal weightage to all the pixel values. So this is Gaussian smoothing, and this is smoothing by average. You can see like this is much more better than this image on the right. Now let's try to understand what will happen if we have noise in our image. Okay, so the original image which I showed you earlier, we try to add like some additive Gaussian noise. And don't confuse this Gaussian noise with Gaussian filter. Gaussian noise is something which we discussed like earlier in the lecture, right? Again, it's coming from Gaussian distribution, but we are adding those values which are coming from the distribution as a noise. Okay, so we have this image which is noisy. If we perform average filtering, we'll get something like this. And if we perform Gaussian smoothing, we get something like this. So I mean, it's hard to say which one is better. But again, in this one, we are kind of losing the texture, right? We are smoothing the image a lot. But in this case, we are getting rid of noise, but it's not that great. But still, we are not losing the fine-grained information which is present in the image. Okay.